Welcome to the following example, which is about a current-carrying wire that creates a magnetic field around it, and then a charge that happens to be moving parallel upwards along this dotted line along the wire. And we would like to know what would be the magnitude and the direction of the magnetic force that would be acting on this charged particle by being in the proximity of the magnetic field of this wire. So, if we were to calculate the magnetic force on that charged particle, hopefully you're thinking of the following formula. Q, in this case Q sub 0, times the velocity, times the magnetic field, times the sine of the angle between the velocity and the magnetic field. And if you're looking at the information given, we've got the charge, we've got the velocity, we don't know the angle quite yet, and we don't know the magnetic field. So what we need to first do is find the magnetic field that exists around this current carrying wire. If you recall, at the beginning of the notes here, you might see that the magnetic fields that are produced by a long straight wire is given by this formula. B equals mu naught I all over 2 pi r. Mu naught is the permeability constant of free space, which is given by this value. So to calculate the magnetic field in example number 10, we're going to need to use that formula first. So B is equal to mu naught I all over 2 pi r. And then we could substitute in. Mu naught is 4 pi times 10 to the power of negative 7 in Tesla meters per amp, multiplied by the current of this wire, which is given as 3 amps. And then we're going to divide by 2 pi times the distance between the wire and where this charged particle is, and that's given as 0.05 meters. Alright, so go ahead and put that into your calculator, and I get an answer of 1.2 times 10 to the power of negative 5 Teslas. So we've just determined the strength of the field at this particular location. But we should also know what the direction of the magnetic field is. So if you recall from the notes earlier up here, you'll see that we can use the right-hand rule to determine the magnetic field around a current-carrying wire. It follows this nice circular pattern, and you can see the compass is pointing in the direction here, tangent at that point. So the magnetic field is determined by using the right-hand rule. You simply grasp the wire with your hand such that your thumb points in the direction of the current and your fingers will curl in the direction of the current. So let's use that. Take number 10 and now grab that wire. Drop your pencil, pretend you're grabbing this wire with your hand, and you should put your thumb in the direction of the current, and you should see that the magnetic field that is induced around this wire is going in this counterclockwise fashion. So at this particular location here, the magnetic field would be tangent to the circle, so it would be pointing right along here. And now you can hopefully see that the velocity of the particle that is running parallel to the wire and the magnetic field, which is tangent to the circle here, makes an angle of 90 degrees to one another. That means that the angle theta is equal to 90 degrees. And so now we're ready to substitute in finding the magnitude of that force. Our charge is given as 6.5 times 10 to the power of negative 6 coulombs. Our velocity is 280 meters per second. The B field we just determined as 1.2 times 10 to the power of negative 5 Teslas. And the angle between the velocity and the B field is 90 degrees. And sine of 90 degrees, hopefully you recall, is just 1. So that should give you an answer of 2.184 times 10 to the power of negative 8 newtons. And the last thing we want to do is use the right-hand rule to figure out the direction of the force. So hopefully you're thinking of the right-hand rule where the B field is your fingers, the direction your fingers are pointing. You're going to point your thumb in the direction of the velocity. So drop your pencil, try it out. And what direction will your palm be facing? So hopefully you're thinking that palm is facing radially inwards. So we'll put that answer in here. And it would continue to be radial inwards if it were to move around at different locations in all places. But in fact, what would happen to this charged particle is as it moves along this line, it wouldn't continue in a straight line. It would actually go towards this wire in a and in fact, as it gets closer, that force would get bigger. So it wouldn't be quite circular, would it? Okay, and that's it for this example.